is kind of about halfway between Adtran and Hudson Alpha, over in the corner of that little section. And I'm going to talk about how my company saved a lot of hours using Docker. So let's just get into it. So why did we start using Docker? We had a couple of projects that could only be built on one machine, and they could only be run on this one server. And to change what machine they were built on, it took a while to gather all of the requirements, and then it took about 6.5 hours to build the requirements, because it was just this giant list of a mix of C++ and Python and Fortran and all kinds of crazy old stuff. And then, even after you had built all the requirements, if you made change to our code, it took another 2.5 hours to build our code and see your updates. That was a problem for me. So I got introduced to one of these projects, and I said, no, I'm not doing this every week. I'm going to do it once. So I tried to find a way to do that. So my first thought was a virtual machine that I left running on my desktop. That's a bad idea. It doesn't work out great, and you will eat a lot of your resources. And then I had a coworker introduce me to Docker, said they'd used it at a past company, tried it out, really liked it. So we wanted to reduce time, so we started out with Docker, and then we started getting new developers added to our team. And they had to set up all the stuff, or they had to set up my Docker setup, my Docker stuff. It turned out that Docker also provided a way to make that simple and make it easier for them to set up. And then the last problem we solved was our project lead is a meteorologist on this, not a developer. They didn't really know much further than running Python space main.py. That was as far as they got as far as development. So providing a Docker container with a simple instruction that they could just run and see everything made things a lot easier for them. So, like I said, we originally had a problem of reproducing build environments. All right, so one machine could run it, one machine could build it. You couldn't do it on your local computer. It took a really long time. So we had that problem, and we had the problem of, this other project, it kind of works on my machine, but I want you to look at it, and now it doesn't work, even though you have basically the same setup. So we started figuring things out with Docker, and Docker solved a lot of those problems by allowing us to pass around our build environment instructions. And it even allowed us to make images of these environments to make sure they're exactly the same. We don't have to worry about a download link changing or a version updating or anything like that. We had the exact same environment. We could pass it around, and we could cut down the build times by passing around those images. So, what exactly is Docker, for anybody that hasn't been introduced to it? It's a software that allows you to create these containers, and they're a lot like virtual machines, but they're lighter weight. So you can run 12 Docker containers in the place of one virtual machine. It's just lighter weight, it's easier to run. And these containers are based on lots of different Linux distributions. Lots of different groups have made containers that you can just download from different Linux distributions. So most of mine are based on Ubuntu or Alpine. Ubuntu because it's what I'm most familiar with in regular development, and Alpine for when I want a really, really small image and I don't want to use hundreds of megabytes. I can use Alpine because it has basically nothing in there. But there's also Debian images, Fedora images, and other different styles of Linux images. And so to start using Docker, you can just run one of those images and run whatever you want from the bash command line, or you can create a Docker file, which is this little config file that says, hey, I want to run these commands when you start up. And this Docker file tells Docker that you want this base image, so maybe I want an Ubuntu image, and then I want these commands run. So I want to install Python 3.7. I want to install pip. I want to get this dependency with pip. Those kind of things. So once you've created that instruction file, Docker will create images for each command you give it. These images can be passed around. It may take 8.5 hours to build the one Docker file if you have a giant amount of stuff in there. But then you can pass somebody this image and it takes them 30 seconds to build it. And it saves a ton of time. That's how we got most of our time savings. But each line of your image is a snapshot of a Docker container, and then it just takes them and layers them. So maybe the first layer is an Ubuntu image, and the next layer is running apt-get to get whatever you want. And usually these images are somewhere in the hundreds of megabytes and they take up space, but you can reduce this size for images by using Alpine Linux or by deleting parts of the image that you really just don't need. And then they can be passed around a little easier. You can also zip them up or tar them, gzip, whatever. And that was the way we passed them around. So they can be saved using Docker and saved to a tar file, and then it just recreates the environment when you load them. So we've got these images, we're passing them around, we've got Docker files, we're saving them in our Git repository so we can access them and reuse them, and realize they were documenting our requirements. So anytime we went in and we had to write, a report to say, okay, these are the things we use for this project, we just went to the Docker file because it had every single line there that said we went and used this, we went and used this, we went and used this. And it made it very easy to keep rerunning the software as we were updating it. I changed, I needed a semicolon on line 32. Well, now I just rerun the image, boom, and my software is running again. I don't have to worry about any dependencies failing or any system updates or anything like that. So it made it where our development environments were the same as our production environments, and it also made it where we didn't have any cost by bouncing between different things like that. So where we found our time savings from that 6.5 hours and 2.5 hours was it reduced our time for setup, it made it easier to put new developers on, and managing complex software development suites, it was just all documented there. We didn't have to worry about, did you remember to download this dependency, or did you remember to change this flag or whatever. It just was there. The biggest lifesaver for me personally was it allowed me to stop work on a piece of software for several months, and when I came back, I just ran one line and it was right back up. So we had a project where my company does small business grants from the government, and we had a phase 1, which is a prototype phase, and so we made this little prototype, put a Docker file around it, built it, sent it out the door. 6 months later, we came back, got another contract to build on top of that. It still worked. It still worked from day one out of the box. I didn't have to go back and figure out what my requirements were. I didn't have to go back and figure out what I'd used or what somebody else had used. It just worked. So Docker reduced our entire system setup to just one command. It was a build and run, done. It made deploying our software a tiny issue. We could throw the Docker container on a server and run it from the server. And it allowed our development teams to focus on the software and not our build process. We set up our build process once and we never had to touch it again. By focusing on that, we made our software better, because if your developers are spending less time bike shedding, they spend more time actually writing code, which makes your code better. So how can this help you? It can help you document your build systems. It can help you stop replicating this same setup over and over. Every time you have a new server, or a new computer, or a new teammate, you stop redoing this. You just run a Docker container. It cuts down on software that takes a long time to build. If you've got a piece of software that takes a long time to build because it pulls in 30 dependencies and it was written in Ada for whatever reason, you can still build it. And you can do it once and then pass around an image of that and never have to build it again. It eliminates a lot of the, well, it worked on my computer, why isn't it working on the server? Or it worked on Jerry's computer, but why isn't it working on mine? Those things don't happen. If you're passing around the same build environment, then you don't have differences in the build, so you have less of that. It makes it where you can build on multiple different platforms without having to stop and think about, how do I get all of my dependencies on that platform? There's also setups where you can cross-compile from Linux to Windows or something like that, where you can build binaries for different systems all using the same little Docker setup. It eliminates that time spent. When I first started, I walked in day one, they handed me a computer and they said, here's a list of things you need to install today. Okay? Wouldn't it be great if it was, here's a computer, this is ready, install Docker and you're done. Saves a lot of time there. And it also creates an isolated environment. At any given time, I've got 4 to 5 projects going on. Those change every 6 months, if not sooner. I need those environments to just be contained. I don't want to pollute my environment with, did I install Python 2.7 and then 3.7 and then over here this one needed 3.3 for whatever reason. I don't have to worry about that. I don't have to worry about whether my CMake is version 3.1 or 3.15. It's all handled. It's in one environment and it's documented in each project. So if I have questions, I just go there. So, who uses Docker? Does anybody in here actually use Docker? Cool. I use it pretty much every day, but there's also a lot of really big companies that use it for different things like deployments or for their CI or for whatever they're doing. So here's just kind of a small list of them, but there's a ton more. If you go look on the internet, there's thousands of companies that use Docker with success from what I've seen. And they use it in things like general development or for deploying server-specific software or for standing up microservices. I know one of the companies on there, I want to say it was GE, actually just stood up like, or no, it was Spotify. Spotify threw up like 300 microservices, all using Docker, and then did some load balancing across it, and that's how they manage a lot of their web services is by using Docker. But it's helpful for legacy builds. We've had some software come in that was written in 1967 and hasn't been updated, and you really have to have very, very specific versions of things to make it even run, much less run correctly. And having a Docker file where it just installs those specific versions, so I don't have to worry about that and worry about, oops, I did update all, and now my computer's out of sync with that code. I can just run it in a Docker container, and I've got what I need, and it runs correctly. We use it for our CI/CD systems. So a lot of people in our company come to our group to say, okay, I need to set up CI/CD for my project. I need testing, I need deployment, I need this all to just work, and I don't want to touch it. And so we say, okay, let's get your project in a Docker container first, and then we can run it all from a Docker container from whatever server we've got sitting over in left field, and it just works. People use it for load balancing, so you can have lots and lots of Docker containers of the same type, and it saves space because Docker containers are small. So you can just run a bunch of these and then send different people to different ones if you're using them for like a web server or something. And then people use them for on-demand systems, so you can spin up a Docker container in a very, very small amount of time, so it makes it easier to create new ones over and over and over again. So, we're at a Python talk, so I'm providing a Python example for a Docker container. So I went through the Django tutorial for creating a website, and their tutorial creates this nice little polling app with lots of bright tie-dye colors on your screen. If you've ever seen it, you'll know what I'm talking about because it looks like it's from the 90s. But it works, and the Python group, or the group behind Python, has created base Docker images that are built on top of, I think, some of them are Ubuntu and some of them are Alpine. And you can just download their image. Then you don't have to install Python. You don't have to install pip. That stuff's just set up and it works. So that's what I did here. I have a Python image that's based on Alpine, so it can be really small. I pull in my requirements. So I may have 50 things I rely on. For this one I had, I think, 2. And then I do a pip install. And then if my requirements doesn't change, I don't have to rerun that command. It caches it, it keeps it. I don't have to go through and do anything else with my requirements. They're installed, I don't have to change them. On line 9, you see I expose a port. This is because I'm running a server, and you can't get to the server without a port being exposed. Docker makes it really easy to expose ports. You can do a bunch of different ones. You can map them differently, so if in your Docker container you're exposing port 43, and in your on your localhost or on your real server or whatever it is you want it to be 8004, you can map those really easily. And then I pull in the rest of my code using a volume. So it just pulls it in, and I can actually change my code on the fly and have it update. I don't have to rerun anything. It's just as good as any hot coding setup I've ever seen with I've been in web development world and app development and even lower level than that. And anything that hot codes, this is one of the best I've seen because it just works. Because you're using your actual file system. So when you change a file on your file system, it's part of your Docker container and it works. And at the end there, the CMD line on line 18, I run a Python server and map it to port 8000 and get it running. So to run this, I've said I run this several times. How do you do it? Docker has really simple setup. So the first one there, I build the image. This goes through, it grabs the Python 3.7 Alpine image, it runs all of the commands I've got, it layers them and it saves them as an image, and I'm calling it PyImage. I've given it a name there. It's saved on your system until you delete it from your system. So if I create the image and then I come back 3 days later, it's still there. Shut down, restart, whatever, it's still there, it still works. Then I run the image. This actually starts it up, boots it up, and runs the command at the end, which runs the server. So I have a server running. I've mapped port 8000 to 8000 just for consistency, so I know where I'm at, and then I can see my server. And then I have a command here that'll let you save it to a tar file, and then you can zip that tar file up, email it to somebody, whoever needs it, maybe put it through a secure site, maybe put it on a USB, hand it to somebody. That is the Docker image that they can now run the Docker run command, and they never have to build it. So if it took you 2 hours to figure out everything and build it, they don't have to do that. It saves a giant amount of time. And then they run Docker load on that tar file to be able to load it up themselves. I also have a C++ example for anybody that works with C++. This one's a little more involved because I needed a library that wasn't just available. So I had to get the Eigen library, it's a linear algebra library, and I had to build that library as part of the Docker container. But once that command on line 15 is done, it's built, and I don't have to go back and build it again. It's just done. I don't have to work with it again. And then I load up my code and I start running with that library. And you can do this for as many libraries as you want. The same commands here, but with this one at the end of the command on the second one, I've given it some arguments to run in a bash shell, so it just runs itself and I don't have to go on the Docker command line and run something from the bash shell. And you can see more examples. I've got a GitHub repo, so I've got C++, Rust, and Python examples, just simple little things that you can do with a Docker file, build it and run it, and save yourself a ton of time, and possibly even give you some hints of how to use it for your company or your code base or whatever it is you need. And if anybody needs this link, I'll send it out at the end. Any questions?
Okay. So, I agree with a lot of stuff you were saying about how Docker just makes stuff like really simple. But what do you think your learning curve was on like how to use Docker itself? Because I found like, as you can see by some of those commands, there's so many different like options to pass, and
yeah.
To me, it's a big learning curve on like how to actually run your Docker.
There was a little bit of a learning curve on how to, specifically for volumes and how volumes work and mounting volumes in a Docker container work. But for me, it was similar to a lot of Linux setups, and I've done a lot with those setups, so it was fairly trivial. But I have had multiple different people that are non-technical, that are outside of, they don't do development, use these. And a lot of times they'll ask, okay, what is this doing? And usually it's a simple answer. So let's see, can I go back? So this one, it has a bunch of different flags there. So the --rm, it just removes the container when you're done with it. When you shut down the container, it removes it so it's not running on your system. The -it gives you a terminal to run things in so you can see the output. The -u sets up user information inside the container so everything is not running as root. The -v mounts a volume, and then the rest of it is the command I want to run. So a lot of times, whoever starts with Docker, if that's you at your company, you do have to spend a little time up front kind of learning, but you don't have to have any of that for Docker to run. You can run Docker without any of those flags, and it will work. But as you learn Docker and as you kind of see what your needs are, a lot of times you'll want one thing to happen, and you'll say, okay, I want this to happen in Docker, and you'll Google, and there'll be a little flag there. You just pass it and do anything. Their documentation is really awesome for a lot of this, and there's also a lot of really good articles on things like Medium and Stack Overflow and stuff like that, where you can just find exactly what you need. For the most part, what I've done is I've been the person that's gone through and put together these instructions, and I'll save them in the README or whatever, and I'll say, this is how you run it with Docker. And then I'll send that to the non-technical person, and I'll say, okay, try this, make sure you can run it, and if you can't, let me know so I can fix my instructions. Any other questions?
Yeah, I have one. So, yeah, sounds like that the Docker is not only just running on the single machine, it's running with cluster
Yes.
machines, right? So my question is how to manage it?
So they have a tool, I think it's called Docker Swarm, and it will allow you to manage multiple machines. I don't use it very often because usually I'm only working with one machine, but they have this tool that you can use to manage a cluster or whatever you have, or multiple different Docker containers. So you can create a swarm that will set up maybe a server and a Postgres database and some other thing, and it'll run them all together. And that's, again, in the Docker documentation. You just look up Docker Swarm and it's there.
Yeah, so for that, I've never used Docker Swarm, but we use DockerCompose.
Yeah, DockerCompose. That's what it's called. Docker Swarms are the groups, but DockerCompose is the command.
You
yeah.
basically just set up a config file and just add your different, they call them services,
Right.
which are your machines and then your different dependencies and things like
Right.
that. And it kind of just handles
Yeah.
all of that for you.
DockerCompose is really excellent if you have lots of different things to set up, lots of different machines, or even if you want to set up your machine, but you want 4 different Docker containers.
So that's a tool, so you guys mentioned this commercial tool.
Yeah, we'll see that in just a minute in the next talk, an example of using Docker.
He's got it. Yeah. It's all of this, I think, is, if I remember correctly, it's commercial, but it's free. So and you can just download DockerCompose and it works. Any other questions? All right, thank you guys.
Before we get to Chris' talk, we have Michael Carroll here giving a quick commercial about some upcoming events.
Yeah. Thank you, Pat. I appreciate the opportunity to come out and speak with y'all today. I was going to come and talk about the NASA Space Apps Challenge coming up here October 18th through the 20th. Have all of you heard of the Space Apps Challenge? Generally, some? Okay. So basically what it is it's a hackathon that happens here. We're going to be doing it over at UAH's I2C building, and then the final presentations are going to happen under the Saturn V in the Space and Rocket Center. So NASA actually puts out a set of challenges. I think there's 27, 28 this year of different like challenge areas that they're facing that they want people to generally hack on. And so they also provide different data resources and NASA open source software resources so that you can create a solution to these challenges. So this year we're going to be giving away $10,000 in prize money. That's going to be split between the high school tier and the professional tier, which is college and up. So we are looking for people to come participate. If you want to be a participant, you can register on our website, SpaceAppsHSV.py. But additionally, we're also looking for mentors and subject matter experts. When I say subject matter experts, it doesn't mean that you have to be like a super expert at NASA geospatial data processing. A lot of the teams, especially as it gets down to the high school level, just need some guidance to sort of stay on the rails over the course of 24 hours, or they have a particular Python problem, or they have a JavaScript problem, and they just need somebody who has a little bit of like professional experience to kind of guide them and help them make decisions on what they should do for their application. So we have, on Friday, we have a pretty awesome speaker lineup. So we're going to have a whole bunch of different panels and speakers from people from within Huntsville, within Marshall, and then also from outside of Huntsville. We've got some YouTube people coming, and I've just been told that we have an astronaut coming on Sunday for the final presentation. So I think it would be a really good extension if you're like looking to try something new or maybe apply your knowledge in a different area. You don't work on NASA data every single day. This would be a fantastic opportunity. Even if you don't want to participate, love to have you come by and just see what's going on. We'll be there all weekend over at the I2C Center. You can always find us. It is SpaceAppsHSV.com. And then I think we have the corresponding, Facebook, Twitter, all of the Instagram, the innumerable social media networks. Any questions? Awesome. I'd love to see you all out there. Love to see you win some money. The challenges are actually already up if you want to like start thinking about it, forming teams, that sort of stuff.
How are the prizes distributed?
I think it's 3-2. No.
Is it on the website?
I don't know if it's on
Duffel
the website.
bags of cash.
Yeah. No. So we
Not 0 to 1 March bill.
yeah. So we'll cut you a check right there. I don't know the exact prize distribution because we've also in the past done a couple kind of like bonus prizes, like people who overcame the most adversity. We had a team one year. It was a high school team. And I think they started with 4 people, and it ended up being just the one girl who had to work all weekend. All of her teammates like abandoned her. So we had like special prizes for people who had, particularly challenging hackathon situations. So I think first prize is going to be like $2,500, but don't hold me to that. It's going to be something along those lines. And any skill level. And if you don't have a team, if you just we can cut a check for up to like 5 people on the team. I generally suggest 3 people on the team because once you get more than 3 programmers in a room for like 24 hours, things go sideways. That's up to you. It's personal preference. But if you don't have a team, but you have a challenge that you're particularly interested in, we're going to be doing sort of matchmaking on Friday and Saturday. One other thing that I forgot to mention. I'm sorry, I'm going to take too much time. We're also doing a resume book for career sponsors this year. So if you are interested in finding a new job or transitioning, or you're in college right now and you're looking for something to do after college, or you're looking for an internship, we'll have a place that you can submit your resume, and those will be distributed to our career sponsors. So we have several companies that are interested in getting really excited, fresh talent, growth mindset type people. And I've been telling them the hackathon is probably the best place that you can find an employee. On the other side, if you're interested in being a career sponsor, come find me. We can talk.
So is that this Friday?
This is October 18th to the 20th, so it's not this Friday, but the next Friday. Yeah, I think it's the Alabama-Tennessee game. It's the only way I can tell time. I'm an Auburn grad, but that's the Alabama team. We had a team come up from Alabama. We had a team come down from Vanderbilt. They made us put the game on the projector last year, so I imagine that it'll happen again this year. So. All right. If you have any questions or you're interested, come chat with me. I'll be right over here. And I'll also say we use Docker everywhere, all the time, in production, in development. It's fantastic. It's the best tool ever.
Thank you, Michael. All right, let's take it over to Chris.
All right. How's everybody doing today?
Relax, the nightmare.
All right. I am Chris Hodges. I work at Adtran. Most of my career was in embedded software development, C++, but I made a move a couple of years ago to get into more of the enterprise software, like server side, kind of cloud computing side. And so I'm excited to share with you some of what I've learned about Docker and Python. I'm on Adtran's tech team, and one of the things we do is we want to help invest in the local tech community here, like NASA does as well, to just help improve and support events like this. So Docker User Group is one of those events that we've got coming up. So November 1st, Adtran will be hosting. Lunch will be provided. You can RSVP on our Meetup site. And looking forward to hearing Pat's talk on brief history of containers. Like all meetups, we need speakers always. And so if you've got any ideas about speaking about something Docker in particular, let me know. And then you can find us on Tech 256, which if you're not familiar with it, is a group on Slack, which I highly recommend. It's got a lot of collaboration going on amongst people in the Huntsville area about all things tech, and we're in the Docker channel there. So I don't know if some of y'all are like me, but as an engineer, I tend to be very optimistic. And so I told Pat a few weeks ago, hey, I'm going to do this talk on microservices in Python. And last night, Pat texted me, he's like, it's about 10 o'clock. He's like, are you ready? And I'm like, yes, I'm putting the finishing touches on things. Little did he know that 2 hours before I was having an existential crisis of if the whole topic of this was relevant or even on track at all. Luckily, that all panned out and we're good. But you know, just like at work, we tend to make over eager estimates. It's easy to do that with talks as well. But part of the motivation for giving this talk was I at Adtran work on network management software, and I'm kind of doing the full stack thing. So I'm working in Scala and Python and Angular, TypeScript, and so also kind of have a focus on DevOps. And so, and then I do the Scrum Master thing in addition to that. So fingers in a bunch of pies, trying to do all of them well, but you know, with full stack, you know, a lot of learning, love to learn. So trying to take that and apply it here in Python with a tool called Celery, and just show what are microservices, what are the trends in the industry, what's the definition of that, what is the tool Celery, just kind of what are the basics of how to use Celery for distributed computing in Python. So we'll go through a real simple hello world with Celery using just a simple task to add some numbers. Then we'll go through an example orchestrating Celery with DockerCompose, and then show how a very key element of DevOps, which is monitoring, how can we monitor Celery while it's running. And I will be honest with you, this is my first talk at an event like this, so I'm not very good at knowing, based on the material that I have, how long that's going to go, but I will do my best to save some time for Q&A at the end, and I've got me a little timer here to keep me on track. Somehow I spent 4 minutes already. Okay, so microservices. Are they a fad? Is it a disruption? Found this study that's about 350 companies worldwide that says 63% of those companies are using microservices in their enterprise applications. And why are they doing this? It's not just because, hey, it's the cool new thing, like they're finding business benefits out of this, right? And so I've listed a few up here. This is kind of market speak, but these are things that the companies reported that they saw through development of applications and microservices. Employees going faster, getting products to market faster, resilience of applications, giving development teams more autonomy, cost savings on infrastructure and other development tools, powering next-gen applications. So this is very much the trend of where we're going as an industry, is having smaller bits of code. To me, a lot of the benefits of microservices are also wrapped up in kind of the whole DevOps movement, right, that I've got. I want to take little bits of code and kind of automate the deployment of it and have good kind of interfaces between groups of code. So microservices are one style of development, and the style of development that's been more prominent in the past has been kind of monolithic application development. So I might have a huge code base of 1 million lines of code, and I compile and run that, and it runs in one process. It may have multiple threads, but just ends up being really big, and that leads to some cons, which we'll talk about. The best definition I've seen for microservices comes from Martin Fowler, a prominent leader in kind of the early Agile days. And so I'll just kind of go through what he's got here. A microservice is an approach to developing a single application as a suite of small services, each running in its own process and communicating with lightweight mechanisms, often an HTTP resource API. These services are built around business capabilities and independently deployable by fully automated deployment machinery. There is a bare minimum of centralized management of these services, which may be written in different programming languages and use different data storage technologies. So this helped for me just kind of put some structure for what is a microservice, what are some of the characteristics of those. So attributes of microservices that are good. They can be asynchronous. They don't have to be. They can also be synchronous. But you know, if you've got a suite of different software talking to each other, you can have it set up such that one doesn't have to depend on a very specific order of request reply in order to communicate amongst the different microservices. Isolation, as we've seen through the previous Docker talk, it's important to know the software that you depend on and have a very controlled environment, and microservices very much depend on that. Autonomicity, basically that kind of I own my function, and I can do that function, and I'm not relying on other functions as much to be able to do what I need to do. So basically the ability to, if another part of the code crashes, I can still run and do the best I can with what's up and running. Single responsibility, this is an important concept in just software architecture, which is having nice modular sections that are responsible for doing one thing and one thing well. Exclusive state, this would cover, hey, as a microservice, I may have to store something somewhere, but I, as a microservice, want to be the exclusive owner of that state that may exist in a database or something, such that there's not multiple people interacting with the same data, like in a database, for example. And then mobility. I want to be able to take that microservice and I want to be able to deploy it in lots of different environments. Could be all local on the same machine, could be spread across a cluster of nodes. I saw this quote and I had to put it in here from a software architecture conference a few years back. Traditional architectures, tools, and products simply won't cut it anymore. We can't make the horse faster anymore, we need cars for where we're going. I think in the industry we're definitely seeing a trend towards breaking these larger applications apart and getting some of the advantages that we talked about earlier. With all things new and shiny, there's pros and cons, right? So pros we've seen with microservices is it does a very good job of enforcing interface boundaries between different pieces of software. There is no calling out to some global variable that's in the middle of the code or good microservices have well-documented interfaces between them. As we saw before, a lot of times that looks like a HTTP API, and you're just doing like a REST kind of interface. But it doesn't have to be that. It's flexible. Another advantage of microservices is I can have an application that is made up of microservices, and the different services can be written in different languages. The only thing that really keeps them the only constraint is that they know how to talk to each other. And so if you're working with something like a REST API that's very standard, that it's not tied down to any specific language. So you can pick the tool that does the best job for what that service needs to do. Independently running microservices leads to easier integration testing because you can quickly stage an environment that has just the services that you need and be able to write tests against them. We talked earlier about keeping one bad part of the application from bringing down the whole thing. It's much easier with microservices to do horizontal scaling where you are able to react to load and be able to scale up more workers, and we'll see that in a little bit. And encourages event-driven and asynchronous architecture. The cons, kind of need a good automated build test pipeline to keep track of how to assemble all these microservices into an application and how to build the app. And that can be somewhat expensive, but you get the benefit of kind of a continuous delivery model where as you're building all these microservices together, you know if you've got good tests around them that you're ready to ship at any moment. Another con would be that calls between services is more expensive than just a simple function call. if I'm making a call in C++ to another function, very little overhead, but if I'm having to serialize, deserialize data and put it out across the network, obviously that introduces some overhead and computing costs there, both on CPU and network resources. And then refactoring service responsibility can be harder than refactoring within a monolith. So as you enforce those interface boundaries and you have those APIs, it can be hard sometimes to change those because you may have customers integrating against those APIs, or one API change may ripple across a number of services. So that's kind of my microservices on monolith take. How am I doing on time? 18 minutes left. Okay, Celery, distributed computing with Python. This is an open source project started in 2009. It's written in Python. To download and run Celery, you can just do pip install Celery if you have pip, which is pretty easy to grab, and that will put it on your machine. So let's talk Celery. The basic building blocks of a Celery application are tasks. And all a task is, it's a class that's created out of any Python callable. So we'll look at an example here in a minute, but basically I just have a function, and that serves, or any kind of callable, that serves as my task. Tasks that block indefinitely could starve out other tasks, or potentially, in the worst case, completely stop a worker. Workers are the executor of the tasks that go into Celery. So this is where people sometimes get frustrated with Celery. I had a talk just with my team this morning of like, oh, Celery, it's that thing that's always, going down. If your tasks are going to block, you could cause a lot of trouble for Celery with its default configuration. So the idea of tasks is be brief, be bright, be gone, which is just do your stuff and get out of the way. No blocking, like in any length of time. It's really supposed to be for short-running tasks, and any work that they need to do needs to be, kind of spawned off, kind of asynchronously the best they can, or just scaling up the number of workers to handle that. So tasks, there's two roles that are defined: what to do when it's called, like to send a message, and what to do on the worker that receives the message. They're not removed from the queue until they're acknowledged by the worker. So the whole task queue is, there's a broker, and we'll go over brokers here in a minute, but the task goes out as a message and it stays in that queue until the worker acknowledges it. And then the good rule with tasks is to improve the performance is make the tasks idempotent, which I had to look up the pronunciation of that. Idempotency is, the best example I could think of is if you've got a remote, your mute button is not idempotent because it depends on the current state of your TV's sound, right? So if I hit the mute button twice, that creates a different result than if I hit the mute button once. A idempotent button would be a dedicated input button where I hit HDMI 1, and it doesn't matter if I hit that 3 or 4 times, it's still going to go to HDMI 1 when I'm done hitting it. So that was my best description of idempotency. But the same concept can apply to tasks in that they do something, and Celery is really set up such that if you can have tasks that if it's okay if the same thing happens more than once, you can tune it to get better performance. All right, so here's a basic task. From Celery, import Celery. We've already pip installed it, so we've got access to it. I create an app, Celery equals tasks, oops, and we give it the name of the module that we're in, and it uses this name to be able to know how to name your tasks. So here's our task here. Def add xy, return x plus y. And we put this little decorator on the function, app.task, and that tells Celery this is a task. And what it's going to do is it's going to name this task tasks.add. Let's see, brokers. Brokers acts as kind of the message queue between the clients that'll be sending the tasks and the workers that'll be executing the tasks. And this is installed and used as a separate application. Celery does not provide this. It's expecting that it's going to be there. and it can optionally be used as a backend to store the results of tasks. I got to move faster. So 2 Celery brokers are available out of the box with good support, RabbitMQ and Redis. They recommend using RabbitMQ if you need better, if you don't want data loss. Redis requires a multi-instance cluster if you want to prevent data loss. So RabbitMQ is very well supported with their docs. So let's go through a quick example here of, so I'm running a Mac. Let's install RabbitMQ, and this will be a good overview because I'm showing you Celery now, but in a second I'm going to show how we use it if we put it in a Docker image. So we just installed RabbitMQ. We've got that running on the machine. Let's see. Oops, let's go to the next slide. All right, so now run Python. We're going to set up a virtual environment. I feel like Python user group, every Python user group needs to show setting up a virtual environment. This separates us from the Python environment that's running on our host machine and allows us to have strict control over the dependencies that we want to add. So we're pip installing Celery, pulling that down. Now we've got Celery on there. Next slide. So this is just soup to nuts how I would start using Celery. All right, so next slide, sorry about that. All right, so next up, we're gonna add the path for RabbitMQ to our path so that we can start it. And RabbitMQ server, we're starting the broker, so this is gonna be that queue that's gonna connect all our clients and our workers to transport the tasks. Here's our tasks.py that we talked about in the previous slide. And in this command here, I'm starting a Celery worker, and he is going to be running in the background. So here's the Celery worker running, and I'm going to go over and start another Python instance, and I'm going to import my task, and then I'm going to call my task. So this is from a separate process I call add.delay, and that adds 2 numbers, and we see it getting run on the worker. Unfortunately, in that previous thing, when I run that add, I don't have a result. I mean, I see it printed out in the worker, but I don't get a result back. So what we did previously was go turn on the back end. This will store the message, and we see here some results. 9, some status is success for adding 4 and 5. Over here on the right is like a client, separate process. We're going to run something and then see on the worker side, we see the task come in and succeed. Let's go to the next slide. So what do we got so far with just Celery and Python? From our Martin Fowler definition, we don't really have a suite of small services. I could build a whole monolithic application with Celery. It could have, thousands of functions it's performing and sending things through Celery as an event queue. So Celery can be useful. Good old Outlook. Thank you, Outlook. No, I don't need my emails up right now. Thank you. Celery could support a monolithic application and act as an event queue for some huge Python application. So we don't have a suite of small services. We are communicating with lightweight mechanisms in that we were sending that add task. We were able to execute that from a different process and be able to see the result come back. But it's not really independently deployable. We did all those steps to install RabbitMQ and get it started and add it to the path and all that fun stuff. All that is what developers would have to do on day one if they want to get started developing with this. Docker to the rescue. All right, so now we're going to start talking a little bit more about how we take Docker and make this more a microservice application. And I've got another example that'll get us there. So already we've got 3 processes running. We talked about RabbitMQ, we got a Celery worker and the Celery client. We skipped daemonization. Celery recommends that if you're going to run these workers, you don't just run it from the command line and have it sitting there where if you exited your terminal it would die. It recommends integrating it with the OS through systemd or init scripts so that it's just a long-running service in the background. So all that is just kind of config of how I would take it from dev to ops and actually run it. And all this varies by OS. So let's go over here a sample app I've put together, which is, let's take a stream of tweets. And I've got a microservice we're going to call stream input. And his only job is to subscribe to a stream of Twitter feeds at about 10 a second. And then message location is going to analyze those tweets, and it's going to pull out just the location in there. There's a lot of other not safe for work stuff that shows up in a Twitter feed, but location is pretty safe. Then on an HTTP interface, I'm going to have a Flask server running with Flask Sync IO, and it's going to show us messages coming across, and it's going to show us the location in real time, and that's going to go to a web server, which we've got running. So those are going to be the 3 microservices, and then we'll have RabbitMQ running as its own Docker container to be that transport. We talked Docker files. Appreciated Kyle's intro. That covers a lot of what's in here. The only thing really to note here is that we've got an environment here that allows us to see Celery as it starts up in the logs, which is just kind of an anomaly that I found online. If you don't have this, then it chops off the beginning of your Celery log. For the copy down here, we're going to copy the code of the different apps into opt app, and then we're going to have a command to run this. So this is a Docker file for one of those microservices, but I need to compose all of those microservices together. And so this is a quick intro to DockerCompose. I've got a version up here that says which version of DockerCompose am I running, and then I've got a list of services in here. I learned a cool trick doing this, which is I can reuse elements between services. So here for environment, I've got a little ampersand in front of env. That stores these environment variables in env so that I can reuse my environment variables across services. So the build, this is going to point to where my Docker file is, and you'll see I've got Docker files in HTTP interface and stream input. It shows here that I'm depending on a RabbitMQ service. It opens a port for my web server. You see port 80 there going to 5000, which is what it is internally mapped. And you see different commands for starting Celery workers on the different services. So here we're saying just concurrency of 1 for that service and message locations. Another service I've got here that's running. Oops. And then I've got RabbitMQ here. This is just going to pull that RabbitMQ install we did. Is just available as a Docker image off the Docker Hub, and I just put this image name in here, and suddenly I can get to RabbitMQ just by referencing it by its service name, RabbitMQ. So any of these containers can talk to RabbitMQ on the just simple host name of RabbitMQ. So let's go through an example here of running DockerCompose up. With that DockerCompose, you see it create the different containers. They're up and running, and now we want to do a build. So it's going to take all that code and it's going to run it, and it's going to create the images for that. And then a DockerCompose down will bring down those containers. One thing to note is that when you do a DockerCompose up to lift up all those containers, it does not by default build a new image. And so that was why we did the round trip there of DockerCompose down, build, and then back up. All right, so some helpful things for debugging. Docker's really good about logs. He has a Docker logs command, and I can just pass it the name of my container. So I'm running this message location server that's part of my microservice Celery kind of DockerCompose. And so we see here the Celery thing coming up. Excuse me. I've got a list of tasks that service is going to listen to, as well as which queues he listens on. And we'll cover queues here in a second. Docker top shows me a list. These are all the processes that are running and which ones are using the most CPU. So that can be very helpful when trying to troubleshoot a microservice. The DockerCompose development workflow, We talked about it not building things by default. This command really helped me as I was building this example. DockerCompose up with a, I think that's supposed to be -- build here, will rebuild all the containers that are part of that DockerCompose. And if you specify a container name after here, it will rebuild just that container and then restart it for you. So that makes it really quick to make changes. All right, so let's go get our Twitter feeds. I'm using something called PubNub here. They've got a public stream that provides Twitter messages at about 10 messages per second. And so we set up a little callback class here. And his job is when he gets a message, he's going to send that task to our little message location service and tell him, here's the message. It's just going to be the full message. He's not doing any transforms on it, just sending it right through. So to start that stream, I go configure it. I'm keeping all of my configuration in environment. And that's a good principle for microservices, is not to hard code configuration within the code. So I've got my PubNub subscribe key and channel that I got from their website in here. I'm going to execute that to start that subscription and get that message stream going. Now, here's the thing that had me in an existential crisis last night, which is how do I run a task if that task is in a different container and I don't have access to that task. So here we see, earlier what we were doing is we would just import the task directly and then call its delay function, which is what causes the task to go out onto the RabbitMQ broker and run. We can't do that here because I want these services to be self-contained and not have to know what are the details of all the tasks, right? I need that single responsibility principle. So we start up an app. Let's just call it our message location app. And then I can do app.sendTask, and I can use the name of the task here. So I need to send it to my HTTP interface service, and I want to call the show user event location task within that. And then KWArgs, I can pass along what are the arguments that I would have. So here I'm just saying send the location, and then I want to parse out of that Twitter stream what is the place and full name there. The other part of getting this working in Celery was how do I get my routes configured such that a microservice only listens for its messages and doesn't consume somebody else's message or task that he doesn't know about and then just throw it on the floor, which is what he does. So each of my apps has, this task routes here where I can wildcard and say if it starts with these things, use this queue. And that helps keep everything separate so that I can send directly to the exact worker in the microservice that I want to send it to. And then we see here the example of how to start a worker and have it listen just to a specific queue. So in those other services, I put this in my DockerCompose, listen to this queue in particular. So here's the front end in Flask with Sync.io that's running, and it just sits there and generates all kinds of random, all over the world kind of places. Seemed a little heavier on Europe as I was doing this about 10 o'clock last night. So this is coming all the way through that stream that I showed you at the beginning through a few services over Celery. And so with Docker, we've been able to get a suite of small services communicating with lightweight mechanisms, independently deployable with Docker. If I may have a liberty of a couple of minutes, monitoring is very important. To get monitoring in, all I have to do is add one service to my DockerCompose. It's called Flower, and I add a port to our environment to make sure that it's using port 8888. Here is a quick demo of monitoring where I can see these are all of my different task queues that I've got, and we see lots of messages. We're counting up 7,000 plus messages. It's about 10 a second. This is a safe for work snapshot of some of the latest Twitter things coming in, and then I get a nice graph of succeeded tasks for the different Celery workers. If I had to do this again, I'd figure out how do I make these Celery workers better named so I don't have to figure that out by some long hex thing. All the source code's available on Microservices Celery on my GitHub repo. All you have to do is clone this. If you've got Docker and DockerCompose, you just run DockerCompose up-d, and you can play around with this. Found a bunch of references. The biggest one I'll highlight is this distributed Python blog. Really does a good job of talking about how to use Celery to do different things. I am out of time for questions. I apologize for that, but feel free to talk to me afterwards if you're interested.
Thanks, Chris.
Thanks.